To measure my liquid, which is distilled water, I use a graduated cylinder. I look at the bottom of the curve to match up with 15 milliliters of distilled water. I pour the water into my 50 ml beaker, and I want to know the temperature, the starting temperature of the water, which should be room temperature because it's been sitting in the classroom. I make sure the bottom of the thermometer isn't touching the glass. And let's see. Temperature is not changing. If I look right at eye level, first thing I'll measure out is the lye. It is very corrosive. I'm wearing gloves, so I'll turn the electronic balance on, and I wait for the numbers to stop. And then I'll put my weighing boat. Our lye is not in very good shape, so we'll have to do our best. I've zeroed the scale. I put my beaker on. I wait, and then I zero it again. Now I need 3.4 grams. Our lye, even in the container, took in water from the environment, so this is not going to be precise. And if I had another one handy, I would do it, but right now this is all we have. So I need 3.4 grams of lye, sodium hydroxide. Now I've gone over, so what I can do is put some back in here, and this will be my waste container. But then also, since I have water in it already, this will not be very precise. 3.55, I'm going to leave it at that, considering that there's some water in there, and that also makes it heavy. When I put this in the water should get warmer. I switch the containers so that I'll pour the water into the lye, and then we should be able to see a exothermic change. So there's our 15 mils of water in 3.4 grams of lye. If I stir it to dissolve, I should get an increase in temperature. I'm stirring it with a stirring stick, and let's see what's happening to our temperature. Sure enough, it's already gone up to 30. This is called an exothermic reaction. So as I stir the lye, I'm actually releasing heat. We're already up to 30. Well, you can read that. Let's see if it keeps going. Notice I'm not stirring with the thermometer. You don't stir with the thermometer. You stir with the proper equipment. Now, the end of the stirring rod is going to be contaminated. So I have to make sure I put it down on a place where I know where it will be so that I don't accidentally touch the wrong side. How would I know if it's completely dissolved? Well, I should see no sediment in the bottom. I still see some of the solid remaining. It should go clear. So I'll just stir, 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 stir. This is creating a solution that would be a strong base. Let's see how our temperature, if it's changed at all. Okay, remember that number, and we'll see if it gets any higher. So I stir, adding kinetic energy, increasing the collision of particles so that we get a nice solution. In the meantime, I can warm up my hot water bath for the lard, to melt the lard. Back to here. Let's see if it's any hotter or if our temperature has stabilized. It doesn't look like it's getting any hotter, so that would be the maximum temperature for a lye solution. I'll zero the scale again, put my beaker on, and zero it. While the lye is now in solution, I need to get 23 grams of lard. So let's go. Again, this lard is from some pork trimmings that we rendered ourselves. Ooh, very close. Oh, too much. Okay, whatever I take out, I can't put back in the original container. So let's see. Put this on a paper towel. 23, we can do it. This stuff looks like candle wax to you. You can actually make candles out of tallow, they called it, tallow candles. So your job as a kid back in the day could be dipping a string in melted lard as it solidifies and makes the candle bigger, one layer at a time, like a gumball. Oh, so close. 23, we need 23. Half of this. Okay, let's try it. Oh, if I breathe on it, it might just go to 23. We can do it. We can do it. Just a tiny bit more. It's getting melted already. Well, folks, I'm gonna say, oh, what are the odds? Okay, great, we've got 23. We need to melt this, so I'm going to put it in the hot water bath. We don't put the lard directly in a beaker, directly on the hot plate. We just want to make sure we don't have a grease fire. So by heating it in this double boiler or hot water bath, we're able to melt it under controlled circumstances so we don't get a grease fire. I've got it on medium heat, and right now it's 4:15, so we'll see how long this takes. Well, that didn't take long at all. 5 minutes, and we just have a tiny bit left. I've washed my stir stick, so if I just give that a little stir, there's no solid oil left. Now, I can take that out with my glove because the top is not that hot. I shut this off and I move it to the side right away. Now, I've got warm oil, and what does it say to do? It says let it cool a little bit until it's still liquid, but warm. So it's too hot right now. So if you think about it, I added lye and this got hot by itself, an exothermic reaction. This heated up on the hot plate and now we're cooling it down. That's not a chemical reaction, it's just cooling off. So once it cools a bit, I'll mix them together. So I made a cold water bath just to help cool it a little faster, but I'll unplug my electrical outlet. Notice I don't pull by the tail. That could pull the wires apart inside. I pull it by the head. There we go. And leave it over there, making sure it doesn't touch the hot plate, which is still hot. And let's see if this is cooled off a little bit. I don't want it to get solid, so I don't want it to get too cold. Just want it to cool in the cold water bath. So I'll try it. Okay, so it feels room temperature, as I pour in the lye, well, what do you think you'll see? What do you observe? What color? What state? You can't smell it, but right now actually it's a little stinky because the lard had gone rancid. So some oils and fats, if over time, will react with oxygen, and they have that, when you smell it, you know it's off. Now I have to stir this for 15 minutes, so we'll come back. Give this a little stir again, see how it's going. It's turning a very dark brown shade, which is a little weird. Oh well, I'll show you what you can do with soap. I wanted to show you the pH of the lye solution. So look at how strong of a base that was. Look at the color of the pH paper and look at the number that it matches up to. We would definitely not be washing our hands with lye. So why do we use it to make soap, to something that we wash our hands with? Well, this really just sat here for a minute. Let's see what the pH is now. Notice I'm using forceps for the pH paper to take it out so I don't contaminate the papers. Well, what do you think? How much different is it now? Not much. So the chemical reaction must take time. In the book, it says to stir for 15 minutes, let it set and thicken, and then stir again for 15 minutes until the mixture thickens. So it's not an instant change that we're going to get. Now, compared to the ones I've made in the past, this one seems a little more waterier or more liquidy than the other one. And I can probably attribute that to not having an accurate amount of lye in there. So let's take a look at some of the ones from last semester. So let's take a look at this soap. We made soap 2 different ways last semester. With one of them, we used lard, and the other one we used oil. So one would be like a vegetarian soap. So if you look inside, they still have like that very nice white soapy color, but this one on the outside looks pretty disgusting. It just dried, that's all. Now if I test with the pH paper, it's like, oh, wait a minute, nothing shows up. That's because it needs to have water in order to test the pH. So let's get this one a little bit wet with water, and we'll see what the pH of this bar of soap is like. We'll let that sit there for a moment. We'll do the same to the other one. Just put a little bit of water on the pH paper, work it into our soap, and we'll see what kind of pH this is. So this soap has been sitting for months. Usually soap has to cure for a while before it's what we would consider safe to use. So let's take a look at this one. What would the pH be? Well, I'll let you decide. Take a look at those colors. And here's, this one was made with lard, and this one was made with vegetable oil. If you remember your pH scale, 7 is neutral. Anything above 7 is a base. Up to 14, 13, depending on what scale you're using. And all these colors, red, orange, yellow, and light green, would be considered colors of an acid. 0 is a strong acid. 13 is a strong base. The bases get weaker as we get closer to 7. These would be weak acids getting stronger, stronger, stronger as you go to the 0. So it looks like these two would be safe to use. Now, let's take a look at this. It's starting to thicken. All right, so that's good. I will keep stirring this and let it set and see what happens to it. But it will take a while before I'm confident in even trying it. But it is definitely getting thick and creamy. So it's doing what it's supposed to do. So the chemical reaction is happening. So it's been half an hour that our soap has been chemically reacting, and it's thickened up quite nicely. So what's been happening? Well, if we think of the oil is a very long molecule made out of mostly carbon and hydrogen. In fact, it's like 3 long molecules, like chains held together at the end, mostly carbon and hydrogen. Now, the sodium hydroxide, sodium is a metal. The hydroxide is a combination of oxygen and hydrogen as a little team. So the sodium breaks away from the hydroxide and it changes the fatty acid, which would be the oil, into a new kind of molecule that has a head and a tail. So if you can imagine a kite, so the kite is the head and then the string with all the ribbons is the tail, or a lollipop or a sucker. So there's like a stick and then a head to it. They behave very differently. The tail or the stick part of the molecule does not like the water. It likes oil. So it likes to hide from water. The head, though, loves the water. So the way these lollipop molecules orient themselves when you put soap in water is all their little tails go together and they surround a glob of grease and they form a structure called a micelle. So if you can imagine a glob of grease where somebody took a bunch of lollipops and stuck them in the glob of grease, that is a micelle, and that would be how the soap behaves in the water. So it doesn't really dissolve grease, but it breaks the grease into tiny little parts, surrounds it with these lollipop molecules, and it rinses down the drain. Well, this is continuing to solidify, and I'll bet you're wondering, what's the pH? Well, I'll get my forceps again. It does not smell good, I'll tell you that right now. Compared to the soaps made in the past, it's just a little off. So if I put this in here, I have to scrape off some of that solid to reveal the color, but it still is, I would say, quite a strong base. Focus. Yeah, sorry it's not in focus and I've got my 2 hands full here. So it takes time. So even after I'm technically like finished and I've set the soap aside to cure, that chemical reaction keeps happening until the soap is a neutral pH and considered safe to use on your skin. So we shall return and look at it later. So here are the soaps we made last semester. They don't look pretty, but they sure work. So we were very successful in our experiment. So I washed my hands with both kinds of soap. And what we want is a nice lather, and for it to not burn my flesh, maybe leave my hands feeling nice and clean. So here's the one made with lard. So if I rub my hands together, hey, I'm getting a little bit of lather, not very much. but it feels nice on my hands and it rinses away. Feels pretty good. How does it feel? Well, it feels clean, squeaky clean. Can you hear that? My hands are not burning. And let's see. They just smell like soap. Okay, let's try the other one. Okay, this one was made with vegetable oil. So again, let's see if it has a little lather to it. Wow, I would say that's a nice lather. My hands are already clean, but that's okay, we'll clean them again. So I let that lather rinse away. And again, my hands feel good. They feel squeaky clean. The soap rinses away very well. No smell whatsoever. So, you know, soap has a smell, but I don't even smell anything with these soaps. I guess you could add fragrance to soaps, but they're lovely. My friend, who's also a teacher, makes soap, and oh my gosh, they are so beautiful. Look what she put in this one. She calls this one Green Planet, pink grapefruit and Chinese cedar. Look at these. They almost look like desserts. So I wish you could smell this. She uses a little bit of gold on the top. And you might thinking, that's soap? Yeah, so you would put this in your bathroom and you would use it. It would make your bathroom smell really nice. Then every time you wash your hands, it would smell just glorious. So you can see she also puts sometimes poppy seeds or coffee grounds or herbs, essential oils into the soap to make it smell really pretty and be super fancy. Now this one is shampoo. So I just wanted to try shampoo so I wouldn't have to have plastic bottles anymore. So this one, she mentioned that I would have to rinse my hair with a diluted vinegar solution after, just to remove any residue. Oh, I'll try it. So there's some beautiful soaps. And it shows just what you can do at home. So the farmers and the pioneers used to make their own soap all the time from water soaked in the ashes from a fireplace and lard or fat that they rendered from an animal that they grew and slaughtered. So, you know, it is an art form to making beautiful soap, but you could make a basic soap. It is dangerous because of the very corrosive base, sodium hydroxide, you have to use. So if you do want to try it, check with your parents. Make sure you are super understanding. Watch lots of videos before you try this because the lye is extremely corrosive. I would say don't try it at home. Wait till you're back at school.